Hello all. Today we will discuss the next topics in magnetic materials. Already in the first session of this magnetic materials, what are the contents in this magnetism and what are the topics presented? We have discussed about that. One more time, what are the contents presented in this magnetism that we have to check here? So these are the contents, basic definitions, origin of magnetism, types of magnetic materials, hysteresis curve, hard and soft magnetic materials, and problems. So in the first module, in the first session of this magnetic materials, I discussed about the basic definitions and the origin of magnetism. Both of these topics are covered here in the first session itself. Now in this second module, we have to discuss about the types of magnetic materials. So how many types of magnetic materials are there? Then what are the properties of those materials? Examples of that magnetic materials, about that we have to describe in this module. So previous to that, what is magnetism? Let we have to see the brief about that definitions here. So we have to go to the previous slides. So what is magnetism means? The phenomenon of attracting magnetic substances like iron, nickel, cobalt, etc. is called the magnetism. So the force of attraction towards magnetic substances like iron, nickel, cobalt, all that force of attraction as the magnetism. And the word magnetism was coined from the name of iron ore, magnetite, whose chemical formula is Fe3O4. So this is the magnetism, and all these basic definitions we have seen in the last module itself. And the second topic, what I discussed in the second topic is to be origin of magnetism. Before going to origin of magnetism also, so what are magnets? Magnets means which get magnetized when placed in an external magnetic field. So otherwise we may give other definition as to be materials which strongly attract the small pieces of iron are known as the magnets. Opposite is the non-magnets, which doesn't get magnetized when placed in an external magnetic field are known as the non-magnetic materials. So like that we described. Then magnetic dipole. Dipole means two equal and opposite poles separated by a small distance. Then magnetic pole is there, magnetic pole strength is there. And what is magnetic field? Flux. What is magnetic flux? Is magnetic flux density, intensity of magnetization, susceptibility. All these basic definitions we have seen in the last module, and we derived the two relations here. What those relations are? The first relation is B is equal to mu naught into H plus I. Using that, we got the relation between two parameters, relative permeability and susceptibility. Mu r is equal to 1 plus xi. Then as the second topic, what is origin of magnetism? How the magnetism is produced within the material, that we have described. So there are two ways to produce magnetism inside the material. One is by supplying an electrical energy. So we have to give the external electrical energy easily. Magnetism is origined within the material. Second general way is the without supplying electrical energy also, some of the materials behaves as the magnets. How it is possible that how these both ways are to be, that already we described in the last module. So first is the by supplying electrical energy. So these are the solenoid coil and Hall effect experiment electromagnetic coils, that also we described. And two, in basic material itself without any external electrical energy also magnetism is produced because of the three magnetic moments which are produced in the material. What those are to be? Orbital magnetic moment, spin magnetic moment, and nuclear spin magnetic moment. So because of these magnetic dipole moments only, any basic material without supplying external electrical energy also, it behaves as the magnet. This all we described in the last class. And coming to this module, where I want to describe about the types of magnetic materials. Then to have this classification, based on what property, these are classified into 5 types that we have to be known. So based on the behavior of magnetic materials once they are placed in the external magnetic field. Whenever the magnetic material it is placed in the external presence of external magnetic field, how the properties it has to show, how their properties are changing. Based on that behavior, all the magnetic materials are classified into 5 types. So those are diamagnetic materials, paramagnetic materials, ferromagnetic, antiferromagnetic and ferrimagnetic materials. This module I have to divide into 2 sections. Like first in the first section, I have to describe dia, para, ferro. So by taking their differences. So we have to describe dia, para, ferro magnetic materials. So by writing their differences in the first section, all this in first section I have to describe. And next later on magnetic materials, antiferromagnetic and ferrimagnetic materials, that in second section we have to describe. So first section we have to take dia, para, ferro. So already I told differences like that we have to describe the properties of this dia, para and ferromagnetic material. Already I have taken these points that only we have to describe here. First, so diamagnetic materials. So what the property of this diamagnetic materials is, diamagnetic substances are those substances which are feebly repelled by a magnet. Once these are placed in the presence of external magnetic field, these are feebly means weakly repelled by external magnetic field. Examples are antimony, bismuth, copper, gold, silver. Like metals are coming under the example for diamagnetic materials. Mercury, alcohol, water, hydrogen, air, argon, etc. These are the examples for diamagnetic materials. Once these diamagnetic materials, when placed in the presence of external magnetic field, they get weakly, feebly repelled by the external magnetic field. Why these are repelled by the external magnetic field? That we have to describe a little bit here. So once we have to consider any example among these. So this is the diamagnetic material, like you have to assume maybe bismuth or copper we have to take. Then how the diamagnetic material in the presence of external, in the absence of external magnetic field, first we have to understand. So no external magnetic field is applied here. So H is equal to, H is magnetic field intensity is equal to 0. No field is applied. H is equal to 0. Then we are considering the diamagnetic material. Then how the diamagnetic material is to be? So permanent dipole moment means here the combination of spin magnetic dipole moment and the orbital magnetic dipole moment. In the case of diamagnetic materials, it is consisting of atoms in such a way that all the electrons are already spin paired. Means spin up is paired with the spin down. How the electrons inside the atoms of diamagnetic materials, it is observed that spin up is to be paired with spin down. Means upward spin is cancelled by downward spin. So net spin magnetic dipole moment is 0 in the case of diamagnetic materials. So no permanent spin dipole moment is existed inside the diamagnetic material. And spin is not existed, then resultant dipole moment, it is coming from only orbital motion of electrons. So orbital dipole moment is existed inside the diamagnetic materials. That too it is observed that weak contribution of orbital dipole moment is existed. Weak, less negligible contribution of orbital dipole moment is existed. Permanent dipole moment symbol is actually circle with arrow is the symbol. Permanent dipole moment. Symbol for permanent dipole moment is circle with arrow. So what the significance of this symbol is to be? Circle is being representing orbital motion and arrow is representing spin motion of the electrons. Already I told in the case of diamagnetic material, net spin dipole moment is not existed. And what is about orbital dipole moment is it is also very less contribution. Less contribution of orbital dipole moment is existed in the inside the diamagnetic material. So no weak contribution in the sense almost it is negligible. So no permanent dipoles are existed inside the diamagnetic material. That's what empty box I represented for this diamagnetic material. These are the properties. This is the behavior of or this is the diamagnetic material in the absence of external magnetic field. No permanent dipoles means no permanent dipole moment is existed. Then once it is placed, it is brought into the presence of external magnetic field. Then what happened to the diamagnetic material? Once we are applying the external magnetic field, which direction we are applying, that direction we have to mention here. Say previously H is equal to 0. Now we are applying external magnetic field towards right side. So this is the direction of external magnetic field. Towards right side we are applying the external magnetic field. Then what happened? So previously no permanent dipoles or no dipole moment is existed inside the dia. Now because of this applied magnetic field, less number of dipoles are induced inside the diamagnetic material. Less number, say I have to draw, these are the dipoles. Only two I have to represent. Two in the sense less number. Less number of dipoles are induced inside the diamagnetic material, and that too, once dipoles are induced, immediately they get repelled by the external magnetic field. So once they are produced, previously no dipoles at all. Now because of external field, less number of dipoles are induced. And once dipoles are induced, they get repelled by the external magnetic field and they move in the opposite direction to the external magnetic field. Already I represented the direction of external magnetic field towards right side, and now these dipoles are moving towards left side. That is why in the first point what we have written, diamagnetic substances are those substances which are feebly repelled by, why they are repelling, in the sense no dipoles are induced. Dipoles once they are induced, so that is why they are to be repelled by the weak strength. That to induced strength is to be weak compared to the external strength. So once it is induced, it immediately gets repelled by the external magnetic field. That is the meaning or justification for the first point. This is the case of diamagnetism. Once they are placed in the external magnetic field, immediately they move in the opposite direction or they get repelled by the external magnetic field. Same point we have to observe in the paramagnetic material. Paramagnetic substances are those substances which are feebly attracted by a magnet. How these are? So the magnetization is to be weak, but how they are behaving here? So they are not repelled, they are moving into the direction or they are attracting. Paramagnetic materials are being attracted by the external magnetic field. What are the examples for this? Are to be aluminium, chromium, alkali and alkaline earth metals, platinum, oxygen, etc. Then what the meaning of this first point? Feebly attracted or weakly attracted towards the external magnetic field. Then how the case of paramagnetic material? Again, I have to take any one paramagnetic material like this. First we have to describe this in the absence of external magnetic field. So that is absence of external magnetic field means H is equal to 0. Even though H is equal to 0 also, some permanent dipoles are existed. In the case of no permanent dipoles are existed, but this situation is different in the case of paramagnetic materials. Already dipoles are existed like this. Dipole symbol already I said, circle with arrow. So like this, less number of permanent dipoles are existed. But what the problem? Dipoles are there, but still it is not at all behaving like a magnet in the absence of external magnetic field. So dipoles are there means dipole moment is there. Definitely it has to behave like magnet. but it is not a strong magnet in the absence of external magnetic field. But the problem here is to be, even though dipoles are there, but they are to be oriented in the random directions. They are aligned in the random directions, so the net magnetization is 0. That is why it is also a weak magnet in the absence of external magnetic field. This is the case in the absence of external magnetic field. But now the same paramagnetic material, if we have to brought in the presence of external magnetic field, so we are applying field in the sense we have to represent the direction, that too towards right side. Magnetic field intensity H, that direction is towards right side. Then what happened? Whatever the dipoles are there, the dipoles immediately they have to get magnetized. They have to take their direction. They have to take their direction into the external magnetic field. All the permanent dipoles takes the rotation into the external magnetic field. Then material gets magnetized. So, but less number of dipoles are there. That is why weak magnetization is existed even though in the presence of external magnetic field. That is the meaning here. Paramagnetic substances, once placed in the external magnetic field, how they are attracted here? They are moving into the direction only. This is towards right side, external magnetic field. All the dipoles are also take their orientation into the direction towards right side only, means attraction is existed. But why feeble in the sense? Less number of dipoles are existed here. So that is the justification for the first point in the paramagnetism. Next, the third type of magnetic material we have to take, that is ferromagnetic material. So ferromagnets are almost we have known, these are the strong magnets. How the first point that we have to see in ferromagnetic materials, ferromagnetic substances are those substances which are strongly attracted by a magnet. So once placed in the external magnetic field, a strong attraction it is existed. Best examples are iron, cobalt, nickel. These three are the best example. Still more rare earth ions are gadolinium, dysprosium, etc. Then what the case of ferromagnetic substance, ferromagnetic material, that we have to understand here. So this always one example we have to consider here. That too I am representing first in the absence of external magnetic field. This is ferromagnetic material. H is equal to 0, means in the absence of external magnetic field, larger number of dipoles are existed. In the absence also, inside the material, larger number of dipoles are existed, and the material itself is to be divided into small regions. Like this, material itself is divided into small regions. So this inside the small regions, how the dipoles are oriented. See here, in the first region, dipole is towards right side. In the second region, dipole is towards down. And the third region, dipole is towards left side. Direction of dipole, only one I represented. Like this, inside the region, dipoles are existed. In one region, they are in the same direction. First region towards right side, second region towards down, then third region towards left side, and fourth region dipoles existed are towards upside. Like that, within one region, dipoles are oriented in the same direction. Different regions, different directions are existed. Then we have the concept of domain in this ferromagnetic material. So what is meant by domain is to be, so domain is the small region in which the dipoles are already aligned in the same direction. Domain is the small region in which dipoles are already aligned in the same direction. But different domains in different directions, they are to be aligned. So in the absence of external magnetic field only, large dipoles are existed. That too, some of the dipoles already they are aligned in the same direction. This is the case of ferromagnet. So that is why dipoles are in the same direction, means dipole movement is existed. So in the absence of field only, ferromagnetic material has to behave like a magnet. But already it is a magnet. Once it is to be brought into the presence of external magnetic field, then what is happened? So H we have to apply external magnetic field, that to direction is also towards right side. then only small strength you have to apply. For small strength of the field only, domain wall movement taken place. No individual rotation, it is not required. Already dipoles are divided into small regions which we call into domains. For domain to domain, wall is existed. Then less strength of field you have to apply. Domain wall movement taken place. And domain permanent dipoles, they have to move into the direction of external magnetic field. For small strength only, domain wall movement taken place. If we have to increase the strength of external magnetic field little bit, all the domains walls has to move into the direction, so the dipoles has to take the direction into the external magnetic field. Material attains the saturation point. So all the domain walls has to take the direction into the direction of external magnetic field. So the dipoles are aligned into the direction of external magnetic field. So the all permanent dipole moment becomes large, in the sense material gets saturated. Saturated means complete magnetization point is easily attained by the ferromagnetic material for the small strength of external magnetic field. Why? Because in the absence only it is a magnet. So once it is brought into the presence of external magnetic field, easily domain wall movement to be taken place. Then all the dipoles has to take the direction into the external magnetic field. Then material gets complete magnetization point. That complete magnetization attained by the material is called saturation point. This is possible for ferromagnetic material. This is the case, that is why we call these materials are strongly attracted by the external magnet. That is the justification for the first point in the ferromagnetic material. Then second point we have to go. So once we have to understand this first point in this, then remaining points are to be followed by the first point only. Second point is, when placed in magnetic field, the lines of diamagnetic materials we are writing here, we are describing. When placed in the external magnetic field, the lines of force tend to avoid the substance. So this is the diamagnetic material we have to consider. Then already we have known these are weakly magnetized, that too they have to move in the opposite direction. They get repelled by the external magnetic field. So that's what, because of that, this diamagnetic material, once it is getting magnetized, means more number of lines of force is allowed by the material per unit area of cross section. But here it is weakly repelled by the external magnetic field. No lines of force, no lines of force are passing through the material. These lines of force tend to avoid. They have to move through the free space only, and these lines of force are rejected by the material, or to be avoided by the diamagnetic substance. So we have to observe the diagram here. No lines of force are to be passing through this diamagnetic material, only one line of force like that. Remaining all are rejected by the diamagnetic material. They are moving or passing through the free space or air. Why? Because these diamagnetic materials are weakly repelled by the external magnetic field. Repelling means not allowing the lines of force. So whatever the lines of force rejected, that are passing through the free space or air. Then paramagnetic substance. These are weakly attracted. Already we have known these are into the direction only, weakly attracted. Then what about lines of force? The lines of force prefer to pass through the substance rather than the air. So as these are attracted by the external magnet, more lines of force that are preferred to pass through the magnet. Now this is the paramagnet. If you observe the diagram, most of the lines of force are passing through the paramagnetic substance compared to air or free space. Compared to air or free space, lines of force are preferred to pass through the paramagnetic material. Then what about this ferromagnetic material? These are the strong magnets definitely. Then bunch of lines of force or crowd of lines of force are to be passing through the material. Then less number of lines of force are passing through the free space or air. Now this is ferromagnetic. Observe this crowd are to be passing through the ferromagnetic material. Remaining all are ejected, remaining all are passing through the free space or air. So that is the case of ferromagnetic material. Next, third point we have to see. So this is third point only, right? In diamagnetic material, we have to see the point here. When a diamagnetic substance is placed in a magnetic field, it is weakly magnetized, that too in the opposite direction to the inducing field or external magnetic field. This already we described in the first point itself. Same point here. Diamagnetic material, once it is placed in the external magnetic field, how it is moving? It is weakly magnetized, that too in the opposite direction. Next, coming to paramagnetic substance, it is placed in the presence of magnetic field, it is weakly magnetized in the direction of the inducing field. Here inducing field is nothing but external magnetic field. External magnetic field. How it is to be moving here? Weakly. Weakly means less number of dipoles are existed, that is why weakly. Weakly magnetized into the direction of external magnetic field. Next, ferromagnetic material. This substance, once placed in a magnetic field, it is strongly magnetized. How the ferromagnetism? We have known already. So, dipoles are divided into domains. Domains means already existed into the same direction. So, that is why it is a magnet in the absence only. Once placed in the external magnetic field, easily domain wall movement taken place. Saturation also possible in the case of ferromagnetic material. That is why strong magnetization is existed in the direction of inducing field. Next, fourth point we have to see in diamagnetism. Induced dipole moment M is small and negative. So, small and negative. Why small? In the sense, less number of dipoles are induced inside the diamagnetic material. Automatically, dipole moment becomes small. Then why it is having negative value means diamagnetic materials are moving in the opposite direction to the inducing field. That is why dipole moment takes the negative value. Opposite direction is indicated by negative sign here. So that is why dipole moment M is small and negative, minus value it is consisting of. Then paramagnetic material, induced dipole moment is here also small, but which value it is consisting here is to be positive value. Positive being represented into the direction of external or inducing field. How the material has to move? Into the direction of inducing field, it has to move or attracted by the magnet. That is why positive value. Why small here is to be less number of dipoles are existed inside the material. Then how the ferromagnetic material? Induced dipole moment M is large and positive. Large means large number of dipoles are existed, and here it is positive. Positive means into the direction or attraction towards the external magnetic field. So that is why it is large and positive. Next, fifth point in diamagnetic material. Then intensity of magnetization I has a small and negative value. Actually, in basic definitions in the magnetic material, that is in the first module itself, basic definitions we have described. There I defined the intensity of magnetization. I is equal to, what the formula is? It is the ratio of magnetic dipole moment per unit volume. I is equal to M by V. I and M are directly proportional to each other. How M should be, likewise I should be. So in the previous point itself, we described about magnetic dipole moment, how it is for diamagnetic material, small and negative. Then automatically, how the intensity of magnetization for the diamagnetic materials is, it is also small and negative. Then coming to paramagnetic materials, intensity of magnetization I is small and positive. So why? Because here M is small and positive, I is also small and positive. Then ferromagnetic material, here intensity of magnetization I is large and positive. Why? Because M is large and positive. Next point in diamagnetic material is magnetic permeability. Mu is always less than unity. Then permeability symbol is mu. We already described about permeability. Permeability is the property by which number of lines of force are allowed by the material to pass through it. Then in previous slide itself, we have described about the number of lines of force. In the case of diamagnetic material, they tend to avoid to pass through the diamagnetic material. Why? Because repulsion is there towards external magnet for the diamagnetic material. So that is why lines of force are not allowed by the material. So less number of lines of force, that too in the opposite direction, then we call it as less than unity. How the mu value we have to define for this diamagnetic materials is mu is less than unity, mu less than 1. Why? Because less number of lines of force, that too not into the direction of external magnetic field, it is getting magnetized. It is repelled by the external magnet. Means it has to move in the opposite direction to the external magnetic field. Then what the case of paramagnetic material is, magnetic permeability, mu is more than unity. In the previous slide, how the diagram for paramagnetic material, even though less number of dipoles are existed, but it is attracted by the external magnet. So more number of lines of force are allowed to pass through the material compared to free space or air. So that is the case of paramagnetic material. So how the permeability is, permeability mu is more than unity, mu greater than 1. That is the paramagnetic material. Then magnetic permeability, mu is large, that is much more than unity. Then this we have to see in previous slide. In previous slide, how ferromagnetic material we described here is to be, it is a strong magnet. That's what we described, that crowd or group of lines of force that are passing through the ferromagnetic material in comparison with the free space or air. So how the value of permeability being describing about the number of lines of force. So magnetic permeability mu is very large, very large, that is much more than unity, greater than, very greater than unity. So that is the case of ferromagnetic material. About lines of force we have described here. Next point in diamagnetic material is about susceptibility we have to describe. Magnetic susceptibility, Xi, actually symbol for susceptibility is Xi, Xi we call, has the value small and negative, small and negative. So we have known in basic definitions, we have seen magnetic susceptibility, Xi is equal to, formula is I by H. It is the ratio of intensity of magnetization to the external magnetic field intensity. So Xi is directly proportional to intensity of magnetization. Then how the value of intensity of magnetization, in same likewise we have to expect susceptibility. So intensity of magnetization is small and negative. So susceptibility is also small and negative. And moreover, qualitative definition for susceptibility also we have known. It represents the easiness of the material towards magnetization. And we have known about diamagnetic material, like it is to be repelled. It is having the weak repulsion towards the external magnet. So no easiness it is expected. So Xi value is going to be small and negative. Why negative it is for diamagnetic means, here we have to know this represents always opposite direction to the inducing field. Then the same point of susceptibility for paramagnetic material is magnetic susceptibility Xi has small and positive value. Then for ferromagnetic material, magnetic susceptibility Xi has large and positive value. It is large and positive value. Then next point in diamagnetic material. So we have to describe how the susceptibility varies with temperature in the next point. So for diamagnetic material, they do not obey Curie's law. Curie's law is not at all followed by the diamagnetic material. That is, their properties do not change with temperature. Even though you increase the temperature, also properties of diamagnetic materials doesn't change. So they doesn't obey Curie's law. Then what is Curie's law? For paramagnetic materials we have to see. Then about that property variation of susceptibility with respect to temperature for paramagnetic material is they obey Curie's law. Paramagnetic materials are obeying Curie's law. That is, they lose their magnetic properties with rise in temperature. Then what is Curie's law? Magnetic susceptibility of a material varies inversely with absolute temperature. So susceptibility Xi is inversely proportional to temperature. If we want to remove this proportionality, then we have to place a constant here, proportionality constant, that we call it as the Curie constant, where C is Curie constant. Curie temperature for iron is 1000 degree Kelvin, for cobalt 1400, for nickel 600 degree Kelvin. So iron, cobalt, nickel are the examples for ferromagnetic material. Next type is the ferromagnetic material. So we are describing this Curie's law for paramagnetic material. These materials are obeying Curie's law, means as the temperature increases, what happened to susceptibility is decreases. Their magnetization property is getting decreased. In the sense, they lose their magnetic properties with rise in temperature. So inversely proportional to temperature, and C is called Curie constant. This is the case of paramagnetism, and we have to see in ferromagnetic material. This material also obeys Curie's law. At a certain temperature called Curie point, they lose ferromagnetic properties and behave like paramagnetic substances. So same like paramagnetic materials, here also ferromagnetic materials obeys Curie's law. Means their susceptibility also inversely proportional to temperature. At a particular Curie temperature, at a particular temperature known as Curie point or Curie temperature, ferro has to behave like paramagnetic substance. So these are the differences among dia, para, ferro. So like that, first section we completed here. So in the second module, we are describing about types of magnetic materials. So how the classification done for magnetic materials is to be, once these magnetic materials are placed in the presence of external magnetic field, how they are behaving. Based on their behavior in the presence of external magnetic field only, they are classified into 5 types: dia, para, ferro, antiferro, and ferrimagnetic materials. Two sections like that we are describing here. In the first section, dia, para, ferro, how the properties we have seen. Then next second section we have to take antiferro and ferrimagnetic materials. So little less number of points are to be there that we have to describe for antiferro. Name itself is indicating these are antiferro. Already ferro we have seen, ferro are the strong magnets. Then opposite to the ferro are called as the antiferromagnetic materials. Antiferromagnetic materials. So in the first point, how the alignment of permanent dipoles, that we have to see. This diagram is representing alignment of permanent dipoles here. The anti-parallel alignment existed. Name itself is indicating anti-parallel alignment of the permanent dipoles is existed in the material as shown below. So anti-parallel alignment means, so this is the antiferromagnetic material like dia, para, ferro, how I explained. So in the absence of external magnetic field, if we have to consider antiferro, how the permanent dipoles means anti-parallel alignment. One is in spin, one dipole moment is in upward direction, other is downward. Then like that, upward, downward, anti-parallel alignment is observed for the permanent dipoles in the case of the antiferromagnetic materials. So this is the case. When anti-parallel alignment is to be there, then upward permanent dipoles are cancelled by the downward permanent dipoles. The two, they are existed equal in magnitude. Their number is equal. How many upward permanent dipoles existed inside the material? Exactly the same number of downward permanent dipole moments are existed. See here, upward are 1, 2, 3, 4. 4 are upward permanent dipoles. These are exactly cancelled by the downward dipoles. 1, 2, 3, 4 equal in magnitude they are existed. So these are cancelled. That is why net magnetization is not existed in the absence of external magnetic field. So this is the case of antiferromagnetism in the absence. But we have to observe the behavior in the presence of external magnetic field. Once external magnetic field, we have to brought this material into the presence of external magnetic field whose direction is towards right side. Then slowly some of the permanent dipoles are to be moving into the direction of external magnetic field. So inside the antiferromagnetic material, weak magnetization is to be existed. So large number of dipoles are to be existed. Large number of dipoles are existed. So once it is placed in the presence of external magnetic field, dipoles has to take the direction. Dipoles has to move into the direction of external magnetic field. So in the absence, it is a weak magnet, but once placed in the presence of external magnetic field, almost all the dipoles take the rotation into the direction of external magnetic field. So that is why strongly attracted towards the external magnetic field. Strong magnetization is existed in the presence of external magnetic field. That is the case here. Then remaining points also we can gather how we have written like dia, para, ferro, like that. Here all these points are not to be there in the slides. So strong attraction towards external magnetic field. Second is to be about the magnetic lines of force we have to describe here. Second point, magnetic lines of force are to be, the strong attraction is there towards means most of the lines of force are passing through the material compared to the free space. So that is the second point what we described for dia. Then third point is to be dipole moment. Dipole moment M is how it is to be large and positive. Large and positive. Why? Because large number of dipoles are existed placed in the external magnetic field. Most of them are to be rotated into the direction. So dipole moment is large and positive. Then next, as dipole moment is large and positive, I is intensity of magnetization is also large and positive. I is large and positive, then susceptibility Xi is also large and positive. Susceptibility also large and positive. Then how the permeability? Permeability means lines of force. Maximum lines of force are passing through the antiferromagnetic material. So mu is greater than 1. How the permeability in the case of antiferromagnetism is to be mu is greater than 1. Then once placed in the external magnetic field, they get magnetized into the direction of inducing field. Into the direction of inducing field. These are the points for the antiferromagnetism. Then how the susceptibility varies in the presence of temperature. Once the temperature is applied, how the susceptibility varies. Then the same points here also written, dipoles are aligned anti-parallel. See here how many upward dipoles are exactly equal to the downward dipoles. When the temperature increases, how the susceptibility variation here that we have to see. When the temperature increases, susceptibility also increases and reaches a maximum at a temperature known as Néel temperature. For previous paramagnetic material and ferromagnetic material, we have seen Curie point. Curie temperature is there. Curie's law they are following, that is inverse proportionality is existed, but it is different for antiferromagnetic materials. Then if we have to plot the graph between temperature versus susceptibility, how it has to vary. As the temperature increases, susceptibility also increases. Then after reaching a certain point, temperature increases also, susceptibility decreases. Then where it attains the maximum value, that the temperature we call it as Néel temperature, whose notation is Tn. Tn represents Néel temperature, beyond which it decreases. So this is the susceptibility variation with temperature, where Tn is called Néel temperature. That is about antiferromagnetism. Antiferromagnetism, exactly opposite to the ferromagnetic material. Next, ferrimagnetic materials. Ferrimagnetic materials, almost similar to the ferromagnetism, is called as the ferrimagnetic. Ferro, how strong it is to be, like that. Similar to ferro is called ferrimagnetic material. First itself, how the dipoles are aligned, that we have to observe in the diagram here. Dipoles are anti-parallel, but the dipoles are not equal in magnitude. In the case of antiferromagnetism, anti-parallel alignment is existed and they are equal in magnitude. But in the case of ferrimagnetic materials, here the dipoles are anti-parallel alignment. It is to be consisting inside the material. but they are not in equal magnitude. See here, how many upward permanent dipoles? 1, 2, 3, 4, 5, 6, 7, 8. 8 are the upward dipoles are there. Then how many downward dipoles here? 1, 2, 3, 4. 4 are the downward dipoles. In the sense, cancellation is there for 4 upward to 4 downward. Still after the cancellation also, some dipole moment is existed. This is the case in the absence. So in the absence also, it is a magnet. Why? Because dipoles are existed, dipole moment is there, and domain concept is also to be there in the ferrimagnetism, similar to the ferro. Then if such material you have to brought into the presence of external magnetic field for small strength only domain wall movement to be taken place. Then little bit if we have to rise the strength of magnetic field, then the all dipoles has to take the rotation into the direction of external magnetic field, and that complete magnetization is also attained by the ferrimagnetic materials. That point is called saturation. This attaining saturation point is important to exhibit hysteresis curve or BH curve. In the next module, we are going to describe about the hysteresis or pH curve. To exhibit this hysteresis curve, definitely the material has to attain two saturation points. So to exhibit this hysteresis curve, two saturation points it has to attain. To get saturation point, complete magnetization it should be done. To get complete magnetization, then domain concept is necessary. Domain concept is existed. Among all 5 types of magnetic materials, dia, para, ferro and antiferro and ferri, only 2 class of magnetic materials are having domains, which those are to be ferro and ferri. Ferri is also having domain concept. So like this, dipoles are arranged. Dipoles are arranged once placed in the external magnetic field, large magnetization, that too in the presence of external magnetic field into the direction. Then we have to describe remaining points here. First point itself is to be large, strongly attracted by the external magnetic field. Strongly, how dia, para, ferro we have written, the same points I am writing. Strongly attracted by the inducing field or external magnetic field. Second point, how the lines of force, a crowd of lines of force, a crowd of lines of force are passing through the ferrimagnetic material. Then how the dipole moment is large and positive. Then fourth point, how the intensity of magnetization is also large and positive. Fifth point, how the susceptibility, it is also large and positive. Then how the permeability is much more greater than unity. Then seventh point, how they have to behave in the presence of external magnetic field. Strongly attracted into the direction, strongly attracted into the direction of external magnetic field. So these are the points. Then what about susceptibility variation with temperature? See here, net magnetization is larger even for small external magnetic field. Susceptibility is positive and very large when the temperature is higher than Tn. So temperature is higher than Tn. Tn means Néel temperature. Néel temperature is higher than Tn, then susceptibility is positive and very large. They behave as paramagnetic and ferromagnetic materials respectively above and below Curie point, Curie temperature. So these ferrimagnetic materials, as usual like ferromagnetic material, they have to obey Curie's law. Their susceptibility also inversely proportional to temperature. So they behave as paramagnetic and ferromagnetic materials respectively above and below Curie temperature. Curie's law is followed by the ferromagnetic materials, ferrimagnetic materials. So these are the properties of ferrimagnetic materials. In the second section, we have seen the antiferromagnetic materials and ferrimagnetic materials. Antiferro means opposite to the ferro, and ferrimagnetic materials are almost similar, consisting of domains, saturation point they can attain, and they will exhibit hysteresis curves, and they will follow the Curie's law, and dipoles are also large, and moving into the direction of external magnetic field. Now this is the with this session we have to close, where in this module or in this second session of magnetic materials we described about the classification of magnetic materials. So in this 5 are there: dia, para, ferro, antiferro and ferrimagnetic materials. Thank you all.